Hello, High Water Studio viewers. Thank you so much for joining us today for another episode of Environmental Engineering Discussion. Today we're actually going to be talking, I say actually like it's hopefully not surprising, today we're going to be talking about something interesting. I think it's one of my favorite discoveries when I was an undergrad. Today we're going to be talking about tank discharge. And this combines differential equations with fluid dynamics in a way I think is really interesting. If you're an engineer or studying to be an engineer, I'm guessing you probably took differential equations, and if you were like me, you probably spent a semester wondering what is the point of all this? Why are we ever going to use this? And actually, in environmental engineering at least, it does come up fairly regularly, or at least a lot of how we solve problems are actually the solutions to differential equations. And one of those is tank discharge. And so it was just really interesting to be able to apply differential equations in a way that actually was useful. Another good application is in concentrations of a continuously stirred tank reactor, as an example there. So in our last video, we actually showed how to model filling a tank with a fluid in Unity. So we actually jumped into Unity. We did a little bit of setting up a scene and doing some C# programming there. And if you're wondering why, if tank discharge is just filling a tank in reverse, well, it's actually quite a bit more difficult or complex, I guess, than that. And so we're going to get into talking about the differences and how to set up the balances and basically solve the differential equation, and then talk about how we can apply this. And hopefully we'll follow up with another video getting back into Unity and using some of these equations in Unity to actually add tank discharge to our existing model. All right, thanks. Let's jump right in. Okay, so here we go. Actually, I had to restart after a little technical difficulty there. And so last time, as I mentioned, we talked about filling a tank. And so before we start talking about tank discharge, let's have a quick little discussion, a little reminder on filling a tank and why tank discharge is not the same as filling a tank. So when we modeled filling a tank, the really important assumption there was that the flow rate remained constant over time. Now, we could change the flow rate. We could open additional valves and double, triple, or flow rate, whatever. But unless we were opening or closing valves, the flow rate remained constant over time. That's the really important aspect of that. And that's a valid, safe assumption if you're assuming, as you probably would, that say you've got a tank here and it's maybe like 1,000 gallons, right? And so it's empty and you want to fill it, right? So okay, so you're going to fill this tank up. Now, if you're hooked up to like a municipal distribution system, somewhere in that system is probably like a 10 million gallon clear well or something, right? And so you're going to have like at H naught, this thing's or at T naught, at your initial time, you have some initial height. Well, once you've filled it up at HT, it's basically the same thing, right? So in other words, you're not really losing any depth of your flow of your fluid column in your clear well over times, and this change here between H and HT is pretty much negligible. In other words, you have this energy gradient between the two that's going to remain constant, and that's why you have a constant flow rate. In discharge, it's going to be a completely different situation. So in tank discharge, your Q naught, your initial flow rate, is going to be higher than your flow rate at any other time. So you're going to have a non-constant flow rate. That is where things get much more complex when you want to try to model the flow rate, the discharge rate, the time to discharge, or basically height at any given time, right? And so if we kind of look at what does that look like, it's basically the opposite. We've got our height initially, and then our height, so at any time, for example, when the tank is empty, right? And then you're going to have some kind of discharge going out where your velocity for the discharge or your flow rate is going to be initially higher than it is any other time. And that's going to be a function of your height. So basically, modeling the height is a function of its own derivative. And so if that's ringing memory bells in your head there, you heard that somewhere before, well, you're probably remembering differential equations, or maybe fluid mechanics or some kind of class where they talked about that. So anytime you have something that's a function of its own derivative, you're talking differential equations, right? So let's go ahead and get in. Without further ado, we're going to start setting up some equations and working through them to see what we can find here. Okay, so your really, basic start to this is that you're going to have a flow rate in and a flow rate out. Pencil's bouncing around, sorry. And that's going to be equal to your accumulation. And you could be talking probably, rate in minus rate out is equal to rate of accumulation. So this is going to be basically, your accumulation is going to be your discharge, right? And so in this case, we're going to say that our flow in is going to be 0. In this example, we want to try to really keep things no more complex than they're already going to be. So we're going to say Q in is equal to 0. And so then we can say that basically Q out is going to be equal to the velocity of the flow out. So basically your water molecules, as they're passing through the orifice leaving the tank, that velocity times the area of your orifice out, your drain hole, basically, right? So, and if you've watched any of our other videos, you've probably heard me say, possibly in every video, well, not every video, but very often, velocity and area, right? So we do a lot of work with flow rates in environmental engineering, and it basically always comes down to your velocity, and your area, your cross-sectional area. And this obviously is no different. And even actually our accumulation, our rate of accumulation, just going to put it like that. This is going to be the area of the tank times the velocity of the surface of the fluid in the tank. So basically our velocity that this surface is moving downward, or you could think of basically the velocity of, or at least the apparent velocity of a water molecule inside the tank, right? Because it's moving down and out. Now, the flow rates of these are going to be equal. So anytime, pretty much anytime you're talking about fluid flows, generally, they're not compressible, and so they're ideal fluids, and you're going to conserve matter so that the flow rates are always going to be the same. Now, you can have different velocities, obviously, and in this case we will, but the flow rates are not going to change. So you could say the flow rate of the tank, which is kind of a little bit weird to say, but basically the velocity times the area is going to be equal to the flow rate out. And that's pretty hopefully apparent that that's going to be your volumetric flow rate as it's leaving the... Did I turn on the... Yeah, okay. As it's leaving the tank, all right? So, excuse me. Okay, so I think the area of the orifice in the tank are pretty apparent. What about the velocity of the tank? Well, that is going to be, as we've mentioned, it's the rate of change of the height of the fluid, basically, right? So the rate of change of the height over time. So from that, we can start, should we go to a new, let's go to a new, no, we'll do one more. So from that, we can start using the Bernoulli equation. Now, before we were looking at conservation of mass, or matter, basically, when we were looking at these flow rates. But now let's look at the conservation of energy using the Bernoulli equation, which is kind of what the Bernoulli equation is, right? It just looks at different ways that energy can exist inside of a, a fluid system. So basically, between, we'll call this like, point, well, that's going to get confusing because we have pressures. We'll just call this A and B. Actually, I don't want to do that either. Let's call this 1 and call this 2. I don't know. All right. So we have a pressure at point, this one is actually, I did that backwards. Actually, let's do this as 1 and this is 2. I think it'll be make more sense that way. All right, so at the pressure at 1, point 1, and then we have half the velocity times the density squared, and then we have the density and gravity and height at point 1. And this is going to be equal, the energy of this whole system is going to be equal to the energy at point 2. You're not going to gain or lose energy, right? It's just going to change form, basically, or how the energy exists. So P2, 1/2 rho V2 squared plus rho G H2, okay? So basically we have pressure, kinetic energy, and potential energy. So in a tank, as the, obviously here we have potential energy at point 1, and then we have hydrostatic pressure at the bottom of the tank. Now, in a free jet, so once this water discharges, it doesn't have a pressure anymore. So you're basically trading pressure for velocity, and going from potential energy to pressure to velocity, basically. All right, so now let's look at some assumptions that we can make that can make this a little bit easier. The assumption we can make is that the pressure at point 1 and the pressure at point 2 are equal. Now, basically, they're both atmospheric pressure. Our pressures, the fluid pressure is 0. And so we have atmospheric pressure, and we're going to assume that between these different heights, there's no real, difference in atmospheric pressure, which I think obviously is generally going to be a fine assumption there. Okay, so P1 equals P2. Oops, there we go. Keep accidentally turning on my eraser there. Okay, P1 equals P2. And then so if we, I did it again. If we rewrite that, basically just removing the pressures, they cancel each other out, and then grouping our variables together, we can rewrite it as V2 squared minus V1 squared is equal to 2 times gravity times the change in elevation. All right, let's go to a new screen. Okay, so actually let's go back for just a second. And a couple of other assumptions that we can make One is that the velocity at point 2 is going to be much higher than the velocity at point 1. And this is because of the differences in the areas, right? So we have a very, relatively large tank area. We have a relatively very small, much smaller area of an orifice here. So we can assume that V2 squared, especially being squared, is going to be much greater than V1 squared. So basically we can neglect the velocity in the tank. And depending on what you're doing, you may or may not want to do that, but I think it's generally going to be fine. Another one we can do is, if we should have saved that, but I'll just real quick rewrite this. So we'll call that 2. If we set our reference, our datum, so our vertical reference, at H2, or at outlet, where H2 is 0. So we're going to call this our vertical datum. Now we can just basically, H2 is 0, so we can pretty much remove it from the equation and just refer to the height in terms of H. So in this case, we have whatever height we are at any time t is just H, right? And so if we rewrite it now, because we've removed those other variables, now we have V2 is equal to the square root of 2gh. Put my notes here. Okay, so if we rewrite that now in terms of our in and out, flow rate, and accumulation, we have the area of our tank. Actually, let me write that down here. So we have our accumulation equal to our flow out is what we're writing here. So we have the rate at which this is emptying and our flow rate out. So kind of like our flow rate down, our flow rate out. It's kind of weird to call that a flow rate, but it basically is. If you think of a tank as a really big pipe, right? That's basically what it is. Okay, and then we can combine our constants together because we have a lot of constants here. Constants. We'll call this K because our area of our tank is going to be, well, at least assume that it's, or actually that's out, but our orifice is going to stay one area. We're not going to have like a valve that people are opening and closing or half closing. It's either fully open or fully closed, basically. And our tank is, perfectly vertical walls. It's not bowing out at all, which it maybe is, but we're going to neglect that. Otherwise, our velocity is going to be changing for more reasons than just the height, right? And that would be more complicated. So if we divide over the area of our tank, and then, of course, gravity is going to be a constant. So really the only thing that's not a constant here is the time, the height, and the derivative of the height. So if we basically put this back in as our as K, then we just have something that looks like this. dH dt, change of height over time, is equal to all these constants times the square root of the height. So now it's looking pretty simple, right? And once we have it like this, we can do, actually let's go ahead I'm going to switch over to one more because now we're going to go into separation. I don't know. Separation of variables. Okay, so we have another video on doing differential equations. If you're interested in getting a little bit more of a walkthrough on differential equations, it's our video on solving non-conservative pollutant transport in the stream, because you have first order linear decay of non-conservative pollutants. So we go through it there. Basically, we're going to use separation of variables, and we're going to get the h's alone and the t's alone, right? Our height and our time, we want to separate that out, do an integral. So we have dh, we have dh over the square root of h, and the integral of negative k, which we'll just call one constant for now, dt. All right, so something, not too super complicated. This would be like h to the negative 1/2. Probably could just Wolfram alpha that one would maybe be the easiest way to do that. So what you wind up with is 2 square roots of h. And of course the integral of dt is t, right? So we have negative k t. And then of course, differential equations. So we've got constants related to our boundary conditions. So this here is going to be our general solution for basically any tank for any boundary conditions. But we can solve because we know that we're going to have an initial height at time 0, right? So if we solve that, so we'll just say solve boundary condition. Where h naught, we have h naught at t naught, right? Okay, so basically we're going to have 2 square roots of h equals negative kt plus c. Well, because t is 0, this completely drops out, and then we already, we're done. We solved for c. We're great. We're amazing. Okay, so c is 2 square roots of h. If we plug that back in as c, and then just rewrite the equation, we're going to have h equals h naught, right? So, whoops, because this should have been h naught. Yep, made a mistake there. Sorry, because obviously we're substituting the initial height at time t, so that should have been our initial height. We still have kt, and then square this. So that's it right there. This is our solution for basically any tank, as long as you either know your initial height and of course your conditions for your tank, which if you remember, k equals area out, so you need to know the area of the orifice. Now, we didn't take into account things like, is it sharp edged or whatever, so that would be, you would have a coefficient there, 2g. So as long as you know those 2 areas and your initial height, then you can solve for your height at any other time t. Now, another thing you could do is, since we know that the tank is empty when h is 0, right? So you could also figure out the total time it takes to drain a tank by putting in 0 for h and then solving for t, or any other height, right? You could solve when there's 1 foot of fluid left, right? And that is it on that lecture. So we're done. Thank you very much for following through there. If you did make it all the way to the end, I appreciate it. I hope it was as interesting as it was when I realized we could actually use differential equations in a way that wasn't just boring busy work. Okay, so If you have any questions, leave them in the comments. If you want to help us out, subscriptions and likes and all that great stuff are wonderful for us. It really helps us get started. And stay tuned for the next part of the video, which will be putting this all in Unity and taking a look at it there. All right, great, thanks.